Thanks. First, is this big enough? Oh, that's probably not big enough. Right around there? Oh, and I should probably change the color. Ooh. Ooh. Oh. That one? Okay. Okay. So, all right. Today we're going to talk about composable reducers in the effects system. But actually, we probably won't even be able to talk about the latter part. I might be able to just kind of mention it for a moment, but while making this talk, I realized those two topics are like big enough that they should have their own talks, and I got too excited about the first part, and it kept on getting longer and longer, and so I think we're just going to probably only be able to cover the first. But I might be able to give you enough information to see what kind of cool stuff can happen after. So interestingly, at the very first Functional Swift conference in 2014, December 2014, so nearly 3 years ago, I talked about something called transducers, just as like a fun way of playing around with functional ideas, just to kind of see how function composition works and stuff like that, which is kind of like a whole other way of talking about this topic. Transducers were things that took reducer functions and spit out whole new reducer functions, and there was like all types of fun compositions there. This will be like doing a whole other type of composition in this world, but the two worlds are of course connected. A reducer is just a function you can feed into like arrays reduce. It's just something that like takes like an A and a B and produces, say, a new A. These things are very kind of central to systems like Elm and Redux, if y'all have played with these things and seen these things, which are systems to manage state. It's not the only way to manage state, but they've been quite successful at it. So it's kind of like a systematic, disciplined study of reducers might make those worlds better. And I kind of think a lot of the stuff I'm going to cover today isn't exactly well documented in the literature. And so I think no matter what, there'll be like some interesting things here. So at a high level, Elm and Redux and all those systems are kind of composed of three pieces. State, which is the full state of your application, everything that could possibly be shown, every little setting, Boolean, and everything. Actions, which is the entire list of everything the user could possibly do in your entire application, every button tap, every scroll, or if that's important. And then a reducer to fold these things together. Take current state, an action comes in, you produce a new state. And that thing just keeps on firing as the user's doing things. And then the Elm then has a nice thing where it can turn state into view, and then a runtime turns that into nice DOM, and it does everything for you. And then over in the iOS world, we just have to listen when new state comes in and just mutate UIKit all over the place and hope it all remains consistent. So that's kind of what we're going to start with. Elm also handles effects. It doesn't even allow you to do side effects. It's a pure functional language. So it provides a system of describing effects. Every pass of the reducer produces a description of every API request you want to make, or reading something from local storage. And then a runtime goes and does that work for you and then dispatches it back. And Redux leaves that entire story blank. It kind of leaves it up to you. How do you want to do side effects? And so there's a lot of fun stuff you can do there, so it's kind of unfortunate that they kind of left it blank. So let's get started. All right. I'm going to live code, but I'm also going to copy and paste quite a bit. So we'll start with the definition of a reducer. I'm going to wrap it up in a struct just so that I can make it a monoid, but really what I would want to do is maybe just a generic type alias, where I could say a reducer is just a function from given some state, given an action that comes in, produces a new state. But Swift doesn't allow you to make functions of this form conform to protocols and stuff like that. And I kind of want to do that, but you could also do this entire story just using a type alias and get rid of one struct. And so a reducer is going to have just a reduce function that takes a state, takes an action, and produces a new state. The cool thing is that this thing already has one form of composition kind of pop out at you, which is it forms a monoid. I'm going to copy and paste what a monoid is. We've talked a lot about that at this conference, last year in particular. There were 2 talks about it. It's a monoid is something that has a binary operation that's associative, so it just knows how to combine things, 2 things into one, and then it has like a given neutral element, something that when you combine it with anything else, you didn't change. And so already reducers, we can make, there's also, I want to print a check mark so that I know when. Okay, so we can already extend the reducer to be a monoid, and this is kind of fun already just to play around. Like, how could we combine 2 reducers? And this would work on reducers for arrays too. If you reduced over an array and you had 2 functions that could do it, as long as the types match up, you'd be able to use this composition to combine those things. So let's see if Swift will stub in some stuff for us. All right, so the empty one. So we have to return a reducer. We're just not going to care about the state we're not going to care about the action that came in. We're only going to look at the state and just return it back. So the neutral element of the monoid is just the thing that it doesn't care what action came in, it's just going to just send the state back. The combining operation has to return a new reducer, and so we have state and action. So we could use the left-hand side to reduce this, and we would get a new state out of that. Then we could use the right-hand side to reduce that new state, but with the same action. And then we could just return that. So we just applied the first reducer and then applied the second reducer. And now we turn this thing into a monoid, pretty quickly. Another fun way to look at this is thinking back to some of the stuff that we discussed at the last conference. Well, if a reducer goes from state action to state, another way you can write this is it goes from action state to state. I mean, you can flip arguments, that's totally fine. You could then curry this so it goes from action to state to state. So given an action, you get a function that goes state to state. And then we discussed last time at the conference that functions from a type to itself, those form a monoid themselves called the endomorphisms of S. And so you have a function from A into the set of self-functions on S. This thing we saw formed a monoid, and we saw that the set of all functions into a monoid from a monoid. And so reducers formed a monoid before we even started writing this down, because of all that. That's kind of a nice thing about abstraction is that I could say in words those things, and we can kind of all be on the same page. But I could also write out the description. Okay. So the next piece is the runtime. The runtime is going to be the thing that in the interface you dispatch the user actions to it, and then the runtime is going to tell you when new state is produced, and you got to go change the UI. Elm does all this magic for you without you ever seeing it. Redux provides something called a store. The store holds the current state, so that when it receives an action, it reduces it and sends it back out. So I'll just prototype very quickly what a store could look like. It's going to have to be a class. It's going to be this God object that lives in the application. It's going to be generic over all the same things. It'll have a reducer. It will have a bunch of subscribers, people who are interested in anytime a new state comes in. So it'll be an array of functions from S to void, and we can call these functions anytime new state comes in. It will also have the current state. And anytime it gets set, we will just loop over the subscribers and notify them of the new state that came in. And then we can provide an initializer for this. I'll just copy and paste. Yeah. Or I could have also done that. All right, so yeah, the store isn't all that complicated. You would then give it a way of dispatching to it. So if you had an action, you would set reset the current state based off of using the reducer to reduce over the current state with that action, reducer.reduce, because it was wrapped in a struct. And then you would also need a way of listening. If you had like a subscribe and you were given a subscriber, which means it's a function that goes from state to nothing. Probably need to make this escaping. And then we can add that to the subscribers, and then maybe, or rather append. And then we could go ahead and give that subscriber the most recent version just of the state, just to make sure it's in sync with stuff. All right, and so it's compiling. And this right here is like all that Redux really is. Like as far as like what Redux provides us, now there's a lot more that should be done because we haven't talked about effects, and that's like the most complicated part of any story. But like this is pretty much it. So let's see why this isn't still quite enough. We want to enhance composition in more ways. In order to see that, we need to like make some sample state and make some sample actions and reducers to see like how these things don't exactly plug together nicely yet. To that, I'll copy over some structs. We're going to think of like a imaginary application of an app that shows like episodes of some kind of show or series or something. And there'll be two tabs. In one tab, you will see a list of all the episodes that are available to you to watch, and you can tap on one to watch it. There'll be a little indicator on the cell of the episode that says whether you've seen it or not. And then there will be, the second tab will be like your account page. It might show some user account information, and then it'll show all the episodes that you've previously watched. And so you just get these two screens. And these are the two structs to represent that user and episode. And then some, sorry. So then we can create some structs that represent like application-specific screens. So we had like the episode state, and it'll show a list of episodes, and then it'll also expose the watched episodes. That way you could show and hide the indicator if you wanted. Then there'll be the account state, which is the other tab, which will provide the logged in user optional to show some like maybe name and stuff like that. Some settings, like whether you want notifications on or not, maybe there's a little toggle there you can hit. And then the watched episodes to show in that list. And that's like the state of the entire application. And then what are all the actions the user can do? On the episode screen, there's not a lot. You can just tap an episode. On the account screen, there's a whole bunch of other things you could do, which is you could log in. Now this is an effect thing, and so we're just gonna, for a moment, say that there's an entire part of the story I'm not talking about, which is how do you do API requests or whatever to get someone authenticated and logged in. They could tap an episode. If they're logged in, they could tap logged out, and they could also toggle notifications on and off. This right here is like, in a nutshell, the entire application, the state and the actions, everything the user can see and everything the user can do. And the reducer is going to glue these things together. So let's write a reducer. All right, nope, sorry, one small thing. This is all the state in the entire application, but we're going to do one more step to unify them, in which we'll just create one big ol' struct of all of our little state structs just put together, and one big ol' enum to put all of the little sub-actions together. And now we got to define a reducer. So let's look at maybe the reducer that would run on the account page. And so this is going to be things that take in all the user actions of logging in, logging out, toggling notifications, and all that stuff. So the only thing you can do is switch on the action and then figure out how to change the state depending on what action was invoked. So I think Swift will help us here. All right. So in the case of logging in, it means we got a user, and that means we want to go into the state and return a new state in which now we have a logged in user, but everything else stayed the same. So user.settings stayed the same, or sorry, not user.settings, state.settings stayed the same, and state.watched episode stayed the same. So we just flipped that one little field and left everything else the same. When they tap on an episode, we will add it to the list of watched episodes. So again, we have to return a count state. We leave the logged in user the same, so that's state.loggedInUser. We leave the settings the same, so state.settings. But then we'll take the state's watched episodes and append that episode to the list of watched episodes. And so now we're accumulating state as the user is tapping things. So already we're getting kind of something out of it. I'll copy and paste, say this one, although it goes pretty much exactly like the other ones. So in the case of logged out, it just means put nil in for the logged in user. And in the case of tapping notifications, it means just to flip that little bool. And here we had to go one layer deeper. We had to return a new account state that then returned a new settings that flipped that little flag. It's compiling. We have our first reducer. First problem is this is getting already messy, having to return all new values all over the place. And so I'm going to do something that typically I really don't like, but Chris really loves. I'm going to use mutation. So I'm going to just create a new playground, though, so I can copy and paste. And we're just going to, as we go through and change things. So this will be part 2. This is part 1. All right, so in part 2, oh, weird. Okay, so in part 2, I'm going to change the reducer to not return a whole new state and instead allow mutation of the state in the reducer. Now this is completely fine because the store is the only thing that ever knows about state. You're not allowed to reach into the store and mutate it other than through a reducer. So why not allow this? It's got to go to void. And then also just in general, anytime you have a function from A to A, this is completely equivalent to a function as a function of in-out A to void. And if you wanted to, you could throw in a parameter B, and then it just becomes like this. Or if it had a return value C and A, it would just become C. So basically, you can move A's from the right side of the arrow over to the left side, but at the cost of making it in-out. And these two worlds are just equivalent. And they compose in the same ways and everything. So let's do it. And now we got to fix everything. So in this case, it just the empty of monoid just means don't do anything. This one's nice. It means now we reduce with S using the left-hand side. And then S was already mutated, so we just reduce with the right-hand side. And now we fix that. So that's nice. Now over here, we can just reduce the current state, and then that's done. And then finally down here, we no longer return anything, and we can just apply a little local mutation. We could just say state dot, this was a login, so logged in user became user. No constructing all new values. Here, we could just say state dot watched episodes plus equals episode. Here, we could say state dot logged in users nil. I'm going to delete these so we can see just how simple stuff got. And then finally here, we can say state dot settings dot notifications on is equal to on. Now that reducer looks very nice, and it still compiles. It's all the same safety and everything. It's just now in our reducer world, we're given an in-out, and we just do the mutation. It's the same as just returning a whole new value, and probably a little bit more efficient. Okay, so that's our first thing, and that right there is going to make it easier for us to see the next kind of composition we want, in which I am going to now paste in an episode reducer, which all it does, all its logic is when you tap an episode, we add it to the watch projects array. I want to compose these to get one master app reducer that understands all app actions, all state and everything, and this would be the thing that my entire application runs off of. So I'm going to say let app reducer equal the episode reducer, and then I can monoidally append it to the account reducer, and then I'm done. Yeah, I'm not, because these two reducers come from completely different worlds. One is focused on only the episode state and the episode actions. The other one is concerned only with the account state and the account actions. You couldn't possibly cram these two things together. We need some way of like lifting them up into a world where they can like speak the same language. So how do we do that? And we have to consider each of these things separately. You lift the state and you lift the actions. All right, so the state is going to be, all right, how can we lift state? So we need a way, so let's like do a thought experiment. You have a reducer that understands just a small piece of substate, and you want to lift it into a world that understands global state. If you have a way of extracting out the substate from the global state, then you could reduce just using that substate, and then you produced a whole new substate, and then you need a way of gluing the substate back into the global state. You need a way of getting and way of setting. Say it with me. Well, you don't have to. It's lenses, of course. It's just, you need getters and setters, and you need, key paths are going to be our biggest source of lenses, but we're going to see that key paths aren't even the whole story, that sometimes we need like honest lenses. So, honest to God lenses. So we're gonna make this lift. We're gonna first start with key paths because it is kind of nice that Swift gives us tons of lots of lenses for free via key paths. So consider a function lift on reducer. So you do reducer.lift, and you lift it using a key path from T to S. T you think of as global state and S as substate. And from that key path, you will get a reducer that understands global state. It'll be a reducer on T. How can we implement this? So we need to return a new reducer. So we get no choice but to start out with, I'm going to do T comma A because it's a reducer on T, so I'll use it like that. So then what can we do? Using T and the key path on T, so we use that state key path to get inside T to get the substate. We could then reduce on that with self, which is a reducer on S, and we mutate like just right there in line, and we use the action that was provided and reducer, let's see, and I only called it A. I think, what am I missing? Where's my mouse? There's a chance that maybe it just needs this. Yeah. I don't know. It seems like I should have gotten that. Maybe the in-out was weird. And this is pretty simple. It's one single line. It's just saying use the key path to go into the global state to get that substate, reduce on that, and then use the key path to like plug, and you mutated that substate. So in a sense, you like set it back into the global state. So now using this, I can say take my episode reducer and lift it with a key path of, I had that global app state, and I'll use the key path of episode state, and now I get a reducer that understands global state, still understands only sub-actions, but understands global state. And then I could take the account episode, or account reducer, and lift it using the app state, account state, and now I get a reducer that understands global state. And then of course what I want to do is say that the entire app reducer is the composition of these two things. But again, it's not going to work because they speak the same language in state, but different languages in actions. We now need a way of lifting the actions so that they can understand global actions. All right? And if state's a struct, and we use lenses for that, and actions are enums, what are we going to use for that? Say it with me. No, you don't have to. Prisms. We need obviously the dual thing. If lenses help pick apart structs and you can like take all the fields and consider them in isolation separately and then do transformations with them and then glue them back into the main struct, the equivalent of that with enums, to be able to pick off branches to inspect them and then put branches back into the enum, is going to be something called prisms. Let me look at my notes. So I'm going to define a new type for prisms, and it'll be generic over A and B, and you'll have two ways of picking apart an enum. You'll have the part where you take the big enum and you try to follow a branch to extract out the associated value on a particular branch. That'll be called preview. So given the big enum, you try to pick out a branch, an associated value at a branch. And then the other way, in which you have a branch, you have an associated value, and of course you can just embed that into the full enum, and that'll be called review. So given a B, you can of course just plug it right into the A. And this is all a prism is as far as we're concerned. One nice thing is in the Swift, it would be great if we had some way of doing this like first class, like keypads give us, but at the very least, Swift gives us the review, because a case in an enum is just a constructor to take associated data, the associated value, and send it right into an enum. So you get that one for free, and we'll see that in a moment. The other one we have to write, and it's a little bit boilerplate, but it's not so bad, and I think it's worth thinking in this nice world, so we'll try to do that. And now we need a lift, the corresponding lift for action, and we got to think out loud how such a thing might work. So another method on reducer, lift, given a prism from B to A. B is the global action and A is the sub-action. From it, I want to get a reducer that understands global actions. So in words, as a thought experiment, if you had a reducer that only understood local actions, if a global action came in, you would try to extract a local action from it. If it succeeded, run the reducer, do your mutation, you're done. If that trying to pluck out that branch failed, which means it's a global action that you have no clue what it could possibly be, just skip the reducing step and just pass along like a no-op. That's precisely what we'll do. We'll literally guard to trying to get, first we'll return a reducer that takes some state S and action B, and we will guard trying to cast that B into an A, but how do we do it? We use the prism to preview it as, well, we don't even need to do it as. That returns an optional, so we're optional guard let unwrapping, and we'll just return. So we'll just let the reducer go by if we couldn't cast that sub-action to a global action via the prism. And I bet it needs this again. Oh yeah, all right, I'm gonna call it action. Thanks. So now, if we get past this guard, we have an action we understand. We might as well now reduce our state with that new action. And now we ran our reducer in local action world that we understand. And so finally, I'm going to have one helper that does both of those right here. And this is kind of nice. That just shows you can lift both at the time, state and action, and you can just kind of see you guard, you mutate, and you key path in, and you move on. All right. So now let's construct some prisms for our world. They will be. I'll just throw them on top or inside app action, which was our global enum of actions. And just so here you see we get review for free because cases are just constructors, and then this is a little bit boilerplate we have to do each time, but it's easy enough. And you see the prisms from app action into sub action, app action into sub action. And now finally, we can do this. So let's just start with one. We will lift not only the state, but the action using the app actions prism for episodes. And then we will compose that with the lifted account reducer, where it not only lifts the state with the account state key path, but it will also lift it with the action coming from the app action prism episode or account. And now it composes. All right, so now we have one single reducer composed of two reducers that only dealt with the things that they were interested in. They were only interested in a very small subset of actions, a very small subset of state, and we got to compose them up into a world that understands all the global stuff, but we don't even need to know about that world. We can always know about our little sub-reducer world. And so I'm going to copy and paste in. I constructed a big thing of state and dispatched some actions, and let's see what it looks like. So here I have created some episodes. I created a store from the app reducer, put a bunch of episodes in, haven't watched any episodes yet. I'm not logged in. I'm not getting notifications. I subscribe and just print some stuff. And then I watch episode 1, watch episode 3, log in, and then turn notifications on. And then I could see all the different state here that was accumulated as I did all these actions. One serious problem, and the serious problem is that I have two watched episodes arrays, one sitting in the first tab where I've got all the episodes, one sitting in another tab where I've got the account. Like clearly those should be in sync. Like if I go and watch on the main screen, like I should mutate the same array that would then drive the other screen. That'd be kind of wonderful to have that deduplication of state and everything. And it turns out like I just haven't factored my state correctly. There's a better way to factor it. And so in order to do that, I need to copy and paste again so we can make some tweaks and then see why we need yet another form of composition to be able to live in that world. So I'm going to copy. I will paste. All right. So, what is the form of composition we? Before I go to 3, actually, I think I wanted to better describe what the problem is. So the problem is in the app state. We've got an array of watched episodes for account state and an array of watched episodes for episode state. We'd like to factor this data, pull out the common denominator or numerator, and stuff it in app state. That way both of these screens can look at a common array of watched things. Like how can we do that? What is preventing us right now from doing such a thing? You want to have almost the ability to have two lenses that look into substate. One would look into like all the episode state, but then also look over here to grab the watched episodes, kind of grab both of those things, package them up into a tuple, and pass that along to the reducer. You can't do this with key paths. Like you need like honest lenses to do this because key paths are not constructible in user world only by compiler magic. So for example, this little fella here, is not possible to construct by us. We cannot implement this function. Say a both operator that says, if you have a key path from A to B and a key path from A to C, why can't we get a key path from A to BC? Where you pluck out the B subpart and the C subpart and you get a tuple, and you of course have getters and setters with that where you just glue both of the pieces in. This thing is not possible to implement with key paths, and and this is only one example of many types of lenses that are just not representable in key path land. So we're going to bring back lenses. We can't only use key paths, and then we'll get this, and then we'll get the final type of composition. So I'll paste in a definition of lens. It's going to be a little bit different than Steven's, but just because I want getters and setters together, but it's all possible to unify all these things also. And I'm also, because we're living in mutation world and we love mutation now, thanks to Chris, it's actually going to be based off of viewing into a subpart and then mutating the subpart. Typically, you're given a set function that has a hole and a part, and you get a new part, or a new hole, but we can derive that from the mutating version. So we'll go with the mutating version as the required component, and then derive the thing that returns the whole new value as like a corollary. So now it's easy to implement this both function.
You're still in the second page, by the way.
Yeah, that's cool. Yeah, thanks. So we can now easily implement this both function. I'll just copy and paste again. Where take a lens from A to B, lens from A to C, get a lens from A to BC. Now, I don't want to go constructing lenses by hand, so I'm going to have a helper that will wrap any key path and turn it into a lens, and then we get easy lenses from every single key path that Swift can generate for us, and so that'll be nice. And so that would look like this. Just the view dives into the key path, the mutating set just takes the whole, goes in with the key path, sets the part, and you're done. It's pretty easy to get that. Let's make sure that we're still compiling. All right, so, and then I'll just show you an example of how we would use this little operator, which is what if we wanted a screen that only showed, for whatever reason, all the episodes that are available and your notification preference, which there's probably no such screen, but here's how you would use it. We have a lens from the full app state into the tuple of array of episodes and a Boolean by bothing, we take both of the key path going into episodes and the key path going into account state, settings, notification on, bundle it up, you get a tuple. Now we've got ways of zooming in on multiple pieces, and you would maybe make overloads of this for taking 3 pieces of substate or 4 pieces or something like that. Now we can finally refactor our code and make the reducers better and keep on exploiting all this composition we're getting. Now we'll, I'm also going to copy and paste. Our lift only understands key paths, so I'll also just make a specific version for lenses so that we can also use lenses when we want to use lenses. So now I'll copy and paste this to page 3. And we will refactor the data and then make use of those little operators to make this better. So watched episodes. No longer will we keep it in the episode state or the account state. It is going to be in the app state as a top level thing so that anyone gets access to it, but you just got to zoom in on that piece and whatever other pieces you're interested in and get them together in a tuple to pass that down. And here's where we run into some limitations with Swift and got to do things that aren't quite what would be really amazing is that so I can make the account reducer understand the account state and an array of episodes or array of episodes. So I was a little worried that tuples wouldn't work with in-out, but it totally works. But what you can't do is destructure this state easily so that you could then pick out the parts. This is literally, if I wanted to get this working, I need to do this and this, this, but get rid of this, and so on, right? And that's not looking fantastic. So what I've been doing, or the best I found, and maybe someone else has a better idea, is to, so the best I've come up with is to put boilerplate at the top of the reducer, unfortunately, which says I will destructure the state into account state and watched episodes state, and then I'll defer plugging that back in to the end. So I have to have this and its inverse, and then I get to treat things very nicely on the inside but at the cost of that boilerplate, unfortunately. If someone sees like better, like come and talk to me, because it kind of feels like there should be, but you can't destructure here, and you can't even name these. Like I can't call this account state so that I could at least computed property on the within the function. Okay, well, let's talk about that soon. All right. I don't want to go off the rails with live coding just yet. So we got that. So I'll just copy and paste this one, which works the exact same. So the episode reducer becomes this. All this stays the same, everything, and then this should now require looking into both of the pieces of state. And I'll also copy and paste that in Word. I'm going kind of long. And so the main app reducer now looks like this, in which you take the account reducer, you lift its state to take both account state and watched episode state. You take the episode reducer to lift it to take both episode state and watched episode state. You also lift the actions as before. We get... So this gives me time to look at a compile error. Oh yeah, I see it, okay. So we have an init that we need to update because we now have different states. So we got to factor this out, but need to put it here. All right, so it ran, and now if we see at the bottom, we're logged in, we have our settings true, and a single array of episodes containing like the 2 episodes we watched, episode 1 and 3. And so, let's see. Okay. And that's, all right, yeah, so now there's like something else. What if, and this I won't code because I think now you can kind of see the pattern, but what is the corresponding story for actions? Like what if you want to understand 2 sets of actions, not just like one action for a particular screen? Well, then you could have like an either operator that takes 2 prisms for sub-actions and combines them into a prism that pokes into either of those branches of sub-actions. So you could just repeat all all the story like all over again, and you get even more ways of composing. But the cool thing is like when you look at it from such a simplified viewpoint of just knowing you want your reducers to look at as little information as possible, and how do you keep on lifting that into more global information, and then how do you get to pluck out multiple pieces of sub-information or multiple sub-actions. All the stuff just kind of starts fitting together nicely, and it kind of feels like you're just stumbling upon something that's existed forever, and like this is just how things are. You're discovering it, you're not like inventing it, and it starts to feel really nice and like you're onto something really good. And then I'll just end very quickly with like a little bit about the effects story, in which we want to describe effects and not do effects. I'll just say that the story is that instead of going from state action to state, we output not only the new state of the interface, and that includes like whether your notification's on or not, and what episodes you've watched, but also like a description of effects that you want to run from that. So during the login process, when you tap login, that's probably going to fire up an effect to maybe bring up a login screen that's going to do some work, and then once it's done with that work, it needs to dispatch back in saying, here's the login result. Like maybe they just canceled the dialog, maybe they succeeded in logging in. And so there's a difference between describing what you want to be done, like API requests or login requests, and then like someone actually running that. And the store can be like the interpreter of this. Like the store is seeing all these effects come in that all the different reducers are producing, and then the runtime, the store can be like, all right, you want me to go write this to the file, to like disk? All right, I'll write this file to the disk. You want me to run this API request and give you the result back? Okay, I'll do that. And so then you get to test very complex effects. And this becomes like, we do a lot of talking about effects, and we've had great talks about ways of managing the effects, and this becomes a fun way of like having like a nice world in which all the effects just kind of pop out for free, like just descriptions, and you have a runtime store running them. Whereas usually we don't have that store. In this world, in the reducer world, you get it very nicely. But that's actually the end of the talk. And so, yeah, so that's composable reducers and kind of effect systems. Yeah. Any questions? Yeah.
Could you elaborate a little bit on the fact that you said that you can do for prisms the same thing that is both for lenses? Because I wasn't really able to do this. How do you do that? What kind of prism you get at the end?
Well, I constructed a few prisms, right? So we had a prism. We've got two prisms here that pick apart branches of an enum. So can you repeat the question again?
How do you implement or at least design a function that is like the both function for lenses?
Sorry. I'll just copy and paste it because I thought maybe I would have time for such a thing. So we're going to start with an either type, which is just the dual of a struct or a tuple, and then we got one of these, which says that if you have a prism from A to B and a prism from A to C, you get a prism from A to either B or C. And that's the exact same of you have a lens from A to B and a lens from A to C, you get a lens from A to B and C. The ands and the ors just flipped and everything just works. And this definition here should work, should compile, it still compiles. And this is how you could have a reducer pick apart, like take multiple sub-actions and still exist in this world and everything.
Okay, so you introduce the either type?
Introduce an either type because we need a way of talking about like ethers or like some types in the in the abstract. Swift doesn't give us this. And then introduce an either type, and then you can write all types of little operators like this for free.
Great.
Any questions?
So, so this there's this correspondence between the reducer state pushing that up into like this more global state and the reader monad, right? So like you can do the same sort of thing where you define your one module has like some dependency and another dependency you can lift it into the.
Mm-hmm.
Could you speak to the underlying unification of these two things and like what is connecting them?
Oh, you're really putting me on the spot. Unifying reducers and the reader monad. I don't know. I'm having trouble coming up. I mean, I'm sure. Yeah, let's talk, and when we inevitably figure it out, we'll yell out so other people can come in here because like I'm just stumped and yeah. Any other questions?
Just like figuring out, maybe do you usually make your state there, your app state, is that just like a global variable?
The store is the state. Yeah. One store for the whole app. I mean, that's just how it's done. The cool thing is like Elm is like just hiding all that from you. You don't even realize that like there's this like very smart runtime doing stuff, and in Redux you're like constructing it and managing it and stuff like that, and that starts to feel gross when you have this global thing that anyone can dispatch to and stuff like that. But yeah, one store, whole app. Any questions? Yeah.
Will you make this available so that we can play around?
Yeah, I think this is already up on my like presentations like GitHub, but I will definitely push like right after this all the newest stuff. Yeah, for sure. And there's actually, well, so Steve and I have been like doing a lot of like fun stuff with this, and we got a whole collection of open source repos where we've been doing web stuff and all types of stuff, and technically some form of this is up there, although that's even more removed from like reality than this might seem, but it still could be interesting. Okay, I think it's good, yeah.